Good morning, good afternoon. Welcome to my presentation with the title Cutting-Edge Silicon Germanium Rectifiers Enhancing Safe Operating Area for High Temperature and High Frequency Applications. My name is Reza Behtash. I'm an Application Marketing Manager at Nexperia in Hamburg, Germany. And this is the agenda of my talk today. I would like to start with the introduction of the new technology, of the silicon germanium technology. The rectifiers based on this technology have a very high thermal stability. This will be explained, and we characterize the switching behavior of the silicon germanium rectifier and compared it to other technologies. This will be also shown. Last but not least is the impact of the switching behavior of the rectifier on the efficiency and also on the electromagnetic emission of the DC-DC converter. Okay, let's start with an overview of the different technologies used for discrete rectifiers. So on this slide, you see the usual technologies based on the voltage range of the application. So Schottky rectifiers are used up to 150 or roughly 200 volts. A Schottky rectifier is based on a metal semiconductor interface. That means there is always a trade-off between the forward voltage drop and the leakage current of the rectifier. The higher the voltage drop, the lower the leakage current and vice versa. That means for high application voltages, you need to utilize a Schottky metal with a very high work function in order to control the leakage current, and this results in a high forward voltage drop. Therefore, at a given voltage, or at around 200 volts, PN rectifiers are used. PN rectifiers are bipolar devices, and that means minority carriers are also contributing to the conduction, and that also means that the switching behavior is affected by the minority carriers. There are different switching speeds. There's a standard type, hyper, and also ultra-fast switching types. At around 650 volts, silicon carbide rectifiers are used. Silicon carbide rectifiers belong to wide bandgap technologies. So you have a wide bandgap resulting in a high breakdown voltage. Another advantage of silicon carbide rectifiers is the excellent thermal stability of the excellent thermal conductance of silicon carbide. So you can dissipate a lot of power in the device. One drawback is the price of the rectifiers. Silicon carbide rectifiers, the technology is grown on silicon carbide substrates, and even the substrate are quite expensive. And currently, on the industrial base, substrates up to 6-inch are available. So for high-end and high-power applications, silicon carbide rectifiers are used. Nevertheless, there are a lot of applications in the range 100 to 200 volts, and in this range, the Schottky rectifiers are suffering from the high leakage current they have, and the PN rectifiers has the disadvantage of a high forward voltage drop. Therefore, Nexperia has recently introduced a new technology called silicon germanium. You might know silicon germanium from RF applications, where silicon germanium devices as HBTs, heterobipolar transistor, are used. Now we have created rectifiers based on silicon germanium in this range, And the silicon germanium combines the advantages of the two worlds. So we have the low VF of the Schottky rectifier and the low leakage current of the PN rectifier, as it is shown also here on this slide. So we are combining the best of both worlds, low VF, and also very important, the fast switching of Schottky diodes and the low leakage and the resulting high thermal stability of the PN rectifiers. So it is really the right choice. I will show this to you in this presentation. Silicon germanium is really the right choice for high ambient temperatures and also for high frequency applications. All products are qualified according to the AEC-Q 101 standard, and currently we have 3 different voltage classes: 120, 150 and 200 volts. Okay, on this slide I would like to present to you very briefly the structure of the silicon germanium. And for comparison, you find the cross-section of the Schottky rectifier on the left-hand side, and the silicon germanium rectifier cross-section is shown on the right-hand side. As you can see, on the left-hand side, the Schottky rectifier consists of the Schottky metal on top, defining the barrier height, and then there's a drift region in light green, and the silicon substrate as the cathode of the Schottky rectifier. In contrast to that, there is a very thin silicon germanium layer between the Schottky metal of the silicon germanium rectifier and the drift region. And this thin layer results in a diffusion current in the structure. There's an additional diffusion current, and this is resulting in a higher current density for a given forward voltage drop. So silicon germanium is a hybrid technology. It's combining the the Schottky rectifier with a PN junction. It's also important to mention that the silicon germanium rectifiers are grown on standard silicon substrates. So they can be manufactured on standard tools and also in a very cost-efficient way. So there is no need for exotic substrates or whatever. Okay, let's continue with the safe operating area. As I mentioned at the beginning, the silicon germanium rectifiers has an extended safe operating area. And what does this mean? So the safe operating area in the data sheet is given this way. It's kind of the D rating of the maximum reverse voltage you can apply to the device. And for Schottky rectifiers, usually you need to reduce the maximum reverse voltage the higher the junction temperature is. And in case of silicon germanium, you can apply almost the maximum reverse voltage up to almost the maximum junction temperature of the device. And in order to clarify this extended safe operating area, I have prepared a measurement sequence, which you see on the next slide. So we have compared a silicon germanium rectifier with a Schottky rectifier. The two devices are put on a thermal chuck upside down, and they are biased in reverse direction. And now we increase the temperature of the thermal chuck. What you see here is the leakage current of the two rectifiers. And at a given temperature, the Schottky rectifier runs into a thermal runaway, so it's getting thermally unstable. while the silicon germanium device continues without an uncontrollable leakage current. So this is what is meant by the extended safe operating area. And if you have a high ambient temperature, for example, in automotive area, or if you have a high power density application, then it is really very important to take care of the safe operating area of the rectifier. And the silicon germanium rectifier has really a wide safe operating area. Okay, let's continue with the switching behavior. So we had a collaboration with the Helmut Schmidt University in Hamburg, and we realized a double pulse test system in order to characterize the switching behavior of the silicon germanium rectifier. So this is shown on the left-hand side. We have been able to realize very high DI/DTs of 1 amp per nanosecond for a DC link voltage of 48 volts. And in order to realize this high speed for a given low voltage, it was necessary to keep the parasitic inductance very low. So it is below 5 nanohenry. And later on, we switched to a DCDC converter so that this PCB was modified so that the shunt resistance was removed and it was converted into a DC-DC converter, converting 48 volts down to 12 volts, and then the impact on the efficiency was also measured and characterized. Okay, on this slide you see an overview of the characterized devices. So we have compared the silicon germanium rectifier to a Schottky, to a trend Schottky rectifier, a planar Schottky rectifiers, and two types of recovery rectifiers with two different designs. All the products are in comparable packages, and I also highlighted here the parasitic capacitance of each product. So you see that there's a huge difference in the parasitic capacitance of each product. And the question is, how does that impact the switching behavior and also later on the efficiency of the DC-DC converter? And this is the outcome of the double pulse test setup. This is now the measurement at 25 degrees C. So the devices are biased in forward direction at 3 amps, and then with a DI/DT of 1 amp per nanosecond, the devices are switched off. And you see that the lowest QRR is seen for the trench product. Surprisingly, since the trench one has the highest parasitic capacitance according to the data sheet. There's also kind of the ringing seen for the trench product. We will see later on the impact on the EMI. At the second place is the silicon germanium product with a very smooth switching. This is shown in blue. And the third one is the planar Schottky rectifier in yellow. And we have a very odd behavior of one PN junction. So this is real. This could be reproduced. And this is at the end an interaction of the switching behavior of the rectifier with the parasitic parts in the circuitry. And the other PN junction highlighted in red is behaving in a normal way. As expected, due to the bipolar nature of the PN rectifiers, they have the highest QRR. Now, if we go to 85 degrees C, you see that we have still the same order and the same tendency. That means the trend Schottky is switching the best with the lowest QRR, and silicon germanium is still at the second place. So that means silicon germanium is very comparable in terms of switching to a planar Schottky rectifier. Therefore, I mentioned at the beginning that silicon germanium has a Schottky-like switching behavior. It is interesting to mention that the QRR of the trend Schottky doesn't match at all if you go from the room temperature to 85 degrees C. This is a huge advantage of the trend Schottky. While for the other technologies, you see an increase in QRR and also in the maximum reverse current. Okay. So what is the impact on the efficiency of the DC-DC converter? So we modified the double pulse PCB and realized a 4812 volt DC-DC converter, and we measured the efficiency of the converter with different rectifiers, and this is shown on this slide. On the left hand side, you see the efficiency for two different forward currents, 3 amps and 1 amp, at a fixed switching frequency of 130 kilohertz. And as expected, the highest efficiency is achieved with the trench Schottky rectifier. And at the second place, there is the silicon germanium and the planar Schottky, and the PN junctions, the PN rectifiers are showing the least efficiency. Now, if we go to higher switching frequencies, as shown on the right-hand side, then the advantage of the lower QRR of silicon germanium rectifier gets visible. The higher the switching frequency, the more pronounced the advantage of silicon germanium. Okay, just to summarize, we can say that silicon germanium has a switching behavior on par with a planar Schottky rectifier, or even better. EMI measurements. We checked also the EMI measurements of the DC-DC converter and the impact of the different technologies. And this is now the radiated emission of the DC-DC converter. We see an increased radiation level for the recovery rectifier with the odd switching behavior. And interestingly, the ringing seen for the trench rectifier is not affecting the EMI level of the DC-DC converter. There's a slight increase seen for the silicon germanium. Okay, now this brings me to the conclusion of my talk. A new technology for rectifiers based on silicon germanium has been realized at Nexperia for the voltage range 100 to 200 volts. Silicon germanium is combining the best of the two worlds, the low leakage of the PN rectifier and the switching of the Schottky rectifier. We saw the lowest QRR and the highest efficiency for the trend Schottky rectifier, and the silicon germanium rectifier was on the same level like a planar Schottky rectifier. And we also saw that there's a huge impact on the PN rectifier design, on the efficiency and also on the switching behavior. Okay, and here you see some references if you want to get more information regarding the silicon germanium technology, please refer to our website, and you can also refer to 2 PCIM publications as shown here on this page for more technical details. Thank you very much.